Hi, today we're going to go through a couple of examples of Markov studied systems. So Markov studied systems, the defining feature is that as you move from state to state in that system, the next state depends on only the current state and not any of the previous states. So we're going to have a look at two examples. One's a linear dynamical system, which is a special case of the Markov system, where the next state is a linear function of the current state. And then we'll go down and have a look at some Q learning. So here's our linear dynamical system, and we've got 4 different states here. And each of these states represent students, a pool of students who might be interested in studying a coding course. So we've got some potential students in this state. They're not studying yet, but there's a 10% chance that they'll take up our course and become studying. There's a 90% chance that they'll just remain in that state. Once they reach the studying state, there's a 65% chance that they'll continue to study in the next period, or a 7% chance that they'll drop that course and never come back and study again. They'll leave the system. There's a 20% chance that they'll complete the course, and there's an 8% chance that they'll drop out and defer their studies to go back into the potential students, and they might come back later. So let's have a look at the code for that. Now we've got 100 time periods here, that's T, and our A is our matrix of states. So columns in this matrix are our current state, so this is P, S, C, and D, and the rows are the next state, and the cells are the probability that you will move from this state to this state. So the probability of moving from P to P is 90%. And the probability of moving from P to S is 10%. And we can see S has got its probabilities in there, and once you reach C, you'll only ever go back to C, and once you reach D, you'll only ever go back to D. This is a single student here, so we're going to feed this vector and say that that student always starts in the potential pool. And then we're going to run that, and we'll have a look at that as a plot over the 100 time periods and see what's happened. So all of the students, 100% of them start in the potential students, and as they go through that loop of 90 and 10%, they move into the studying group, the study state, and then they'll start completing the course or dropping out until everyone has left the studying and potential students, and they've either dropped the course or they've completed the course. And we can see that dropped course is about 25%, 26%, and the completed course is about 74%, and that is exactly the same ratio here as the 20% and the 7% probabilities. And that's because by the time that the time periods are over, everyone has gone through either of these two. So there's a quiz example. Now we'll have a quick look at Q learning. And in Q learning, we use states as, in this particular example, we're using them as levels of enthusiasm to study the course. And we want to increase that enthusiasm by offering scholarships. So that's an action that we can take. And each one of those actions has a cost and a reward. So our cost is between 0 and 2.0, and our reward is that our interest in our course increases to 75%. Rather than the standard flip of a coin, 50%. This is the algorithm that updates our, it's our learning algorithm that updates our choice of whether we offer the offer the scholarship or not. And we've got a bunch of variables here that we feed into that algorithm, and here they are down here. So our alpha is our learning rate, a discount factor, and these are our two rewards, so our 50% if we haven't got the scholarship, and our 75% if we do, our 10% levels. You can see that down here is basically this algorithm, and once we learn that and graph that, and we're going to do that for about 1,000 times, we come out with this graph, and this is our Q matrix graph. Our matrix basically, with our enthusiasm levels in this column, which are our states, and our costs for our actions on this are our rows, And in these cells, this is our reward as to whether we should do the action or not at this date. So at 0 cost, we should always, red is always offer the scholarship, and at each level. Whereas at level 1, we wouldn't offer it at level 3 and 4 because our learning algorithm has told us that we don't get enough benefit out of offering it at those levels. And you can see as the cost goes up, there's more blue, so there's more times where we're told not to offer the scholarship compared to when the scholarship is cheaper. And if we increase the time period and we take longer and we let the rewards flow through a bit further, we get more and more red. So you can see here it's only a little bit of blue up the end at the really expensive points, and when we run it for 10 to the 7 times, it's basically all red except for a little strip of blue around the edges just to say don't do it there. So that was really quick, but I hope you got some sort of oversight of Markov chains. Thank you.